also, yes.
Good.
Yep.
Yeah.
And also in,
And so what we see with Lewis acids is that they form a covalent bond with another species by accepting an electron pair. Whoop. Accepting an electron pair. So now we're thinking about the movement of electrons. A Lewis base is going to form a covalent bond by donating an electron pair. So E minus for electron. Sometimes it can be really difficult to identify a Lewis acid or a base. So one way to do that is to draw Lewis structures. Okay, so remember drawing a structure for a molecule or a compound, adding the covalent bonds and the extra lone pairs, the dots around different atoms. So we're going to take a look at that. So here's our first example. We are going to draw some Lewis structures for the reactants and the products. And so actually, let's have you try that. I'm going to come back to that here in a second. Take a couple minutes, talk with your neighbor. Draw the Lewis structures for ammonia, HCl, ammonium, which is NH4 plus, and chloride ion. All right, so see if you all can remember how to do that. Do we remember how to draw Lewis structures? Seen some yes nods. Okay. I'll just give you a few more seconds and then we'll join up and write them all out. All right. So the first step in drawing Lewis structures is knowing how many valence electrons each atom in the molecule or the compound is going to contribute to that Lewis structure. And so we do that with the periodic table, which are almost covered up by the screens. That's fun. So nitrogen is going to have 5 valence electrons. Hydrogen is going to have 1. In ammonia, there are 3 hydrogens, so we're going to multiply that by 3. Add those up, and we should get 8 valence electrons to put somewhere on our molecule. So we can draw out central atom, nitrogen in this case. We need to covalently bond 3 hydrogens. And so each covalent bond is going to represent 2 electrons. So that gives us a total of 6. And then we have 2 left over, and so those are going to be lone pairs, a lone pair on the nitrogen. Everyone okay with that? Cool. So then we have HCl. Hydrogen has 1 valence electron, chlorine has 7. We're going to draw a bond between the hydrogen and the chlorine. That gives us 2. We need 6 electrons. We're going to put 3 lone pairs around the chlorine. Okay. Now, one thing about HCl is that when we put it in solution, it completely dissociates. So we end up with H plus, which is not going to have any valence electrons, and Cl minus, which is going to have 8 valence electrons. That minus sign gives us an extra electron. Remember that? That's going to be important, okay? For the ammonium, we have 5 valence electrons from nitrogen, 4 in total from the hydrogens, minus 1 because we have a plus 1 charge. So that gives us 8 valence electrons. And so when we draw our covalent bonds between the nitrogens and the hydrogens, we're going to end up with a structure that looks like this. There are no lone pairs on the nitrogen. And then the chloride ion, we already drew. I put it in brackets. I think this is the appropriate way of drawing a charged species. Actually, I should do that here. When we do Lewis structures. Okay, so now we know where our valence electrons are, and now we can keep better track of where they're going to go during the reaction. So what bond is formed? What's that? Hydrogen bonded to what? I don't know who said that. Bonded to a nitrogen, right? So essentially we're going to form a bond between this nitrogen and the hydrogen from the HCl. Okay? So really the only 2 species we need to think about when we're looking at this reaction are these 2. And because we're using the Lewis definition of acids and bases, we know that a Lewis acid is going to accept an electron pair, and a Lewis base is going to donate an electron pair. So the species that's boxed in red that has a lone pair to donate is the ammonia. Okay, so these electrons are going to be donated to the hydrogen to form a covalent bond, which means that the H plus accepts an electron pair. And so the NH3 donates. And so we could probably have guessed that our H plus was going to be the acid, and that the ammonia, maybe you know that this is a base. Okay. It's a weak base. So I think that the Lewis definitions of acids and bases is the most complicated, in part because you do need to see the structures. I think we're going to look at one more example that maybe is a little bit more clear. But do you have questions on that? Yeah. that that's the Lewis acid. Great. That's a good question. In this case, I think it is pretty obvious what species is the acid, but that's not always going to be the case. So let's see what. What's that? How have I been?
Yeah.
Oh, okay.
All right.
Yeah. How are you?
I've had, I mean, for today I had better days, but
Yeah.
no, I just have a lot of stuff to handle this weekend. And I was like, well, that's what we're talking about. I just feel academically like I'm catching up a little, but as I'm catching up, more things get added. I was like, oh, great.
Yeah.
But I really.
Okay. We're going to zoom in here to, actually, let's draw it out. So let's take an example where we have iron 3 plus 6 H2O forming a complex ion like this. Okay. So what this complex ion means is that iron is the center atom, and around it are 6 water molecules. Like so. And overall, there's a 3+ charge on this species. So now, which one's the acid and which one's the base? That gets harder, right? So now it makes sense to really draw those Lewis structures. The iron one is easy, okay? The iron 3+ is easy. We can figure out how many valence electrons are on the iron. We can figure out what the Lewis structure looks like of water. Okay, and maybe we can make a guess. Where are we with iron? Iron 3+. 3. Just gonna do it like this. We can make a guess based on these Lewis structures where the lone pair of electrons is going to come from, that's going to be donated, and which species is going to accept it. Okay. So we only have a lone pair on the water. So this is going to be our Lewis base, and this is going to be our Lewis acid. Lewis acid accepts, Lewis base donates. Yes?
This might seem like kind of common sense, but I just want to clarify. Does the molecule in its Lewis structure have to have a lone pair on it in order for it to be
Does the molecule have to have a lone pair on it in order to be a Lewis base? It has to be able to get rid of some valence electrons. Typically, that is by valence electrons. I can't say completely that's the only way, because I don't have enough organic chemistry knowledge to say that completely, but that is most likely the case.
I guess for like this course.
For this course, absolutely.
Okay.
Yeah.
Is it fixture that whichever one has the lone pair will be the space?
Yes. Yeah. So whatever has the lone pair is going to be the Lewis base. And often you're going to see this type of reaction. So you're going to have the formation of a complex ion with some metal, okay? That's typically what you're going to end up seeing. What else do I have on this slide? So in general, what we can say is that cations with a charge, so like a 3+ charge with the iron, are strongly attracted to water molecules, and they act as Lewis acids. So that's the metals acting as Lewis acids. Here's a few different examples of cations that will act as Lewis acids. Iron 2+, zinc 2+, nickel, iron 3+, chromium 3+, and aluminum 3+. This other figure here actually takes this one step further, where now the complex ion of iron hexaaqua complex ion is then reacting with another water molecule to form an acidic solution. But I think that's beyond where we need to be right now at this point. So we're going to skip over that. So you don't need to know exactly what's going on in that figure, okay? But do know how to tell Lewis acids and bases in the general form, okay? We might come back to. Yes?
Are Lewis acids and bases as well as the other two, like type 3, we're not always going to be determined from the reactants?
Yeah, so all the different types of acids and bases are going to be determined by looking at what's reacting. The other thing you can kind of do now is, okay, so we have this reaction, the iron 2+ in the water. If you were to look at that and use the Arrhenius definition or the Bronsted-Lowry definition, you wouldn't be able to tell that iron is acting as an acid. There's no H+ formed in the solution, and the proton's not being donated. So that's why we are including this Lewis definition as one that explains acids. But if you go back now and look at every other acid-base reaction that we talked about, you could identify it as a Lewis acid or a Lewis base. That would fall into those categories. Does that make sense? Okay. All right, so a little summary here of your 3 definitions of acids and bases. We've talked about this quite a bit now. Arrhenius, H+ and OH- are what we're looking for. Bronsted-Lowry, where the proton's going, and Lewis, where are the electrons going. Okay. All right, so we need to talk a little bit about the pH scale. I showed you a problem last time where we calculated the pH of a neutral solution at a higher temperature, higher than 25 degrees, 50 degrees C. And what we saw was that the pH at a neutral temperature was then less than 7. So what the point of that was is that the fact that we call pH 7 neutral, that's only at room temperature, 25 degrees Celsius. And this a 7 is just a number that we've given it based on the fact that when we put water, when water sits on the beginning beaker or in a cup or whatever it may be, it dissociates somewhat, just a tiny amount, into H+ and OH-. And the concentration of those ions is small, times 10⁻⁷. When we are at neutral at 25 degrees C, the pH is 7, okay? Because the pH is given by this equation, pH equals minus the log of H+. One other thing to point out is that if you're doing homework problems or exam problems or recitation problems, if the temperature isn't specified, assume it's 25 degrees Celsius, so that you can assume that these types of things. Kw is 1 times 10⁻⁴, that kind of thing, okay? So to calculate pH, we need to do minus the log of the H+ concentration. So at 25 degrees C, the pH equals 7.00. Have we done sig figs with pH yet in lab? No, you're gonna love it. I'm kidding. I don't know actually how much you do that in lab, but the sig figs rule for logs is slightly different than the other rules. So I will just touch on it briefly, and please know that I care very little. But there's two significant figures in this number here, 1.0. The significant figures only show up in the decimal place of the pH. Okay, so that's why I've included 2 digits after the decimal. Those are both significant even though they're zeros. Okay. This first number is essentially a placeholder. It comes in from the exponent. Yes?
So just to clarify what you're saying, is it like the number of decimal places, number of sig figs, the number of the log?
Yes.
Okay.
The number of sig figs in the concentration is the number of sig figs you put after the decimal in the pH. Yeah. Other questions? Okay. We calculated last time that at 25 degrees Celsius, the H plus concentration and the OH minus concentration were equal. They're both 1 times 10 to the minus 7 molar. Okay. We use the pH scale most typically, but we can take the minus the log of anything and put a small p in front of it, and we call it whatever. Okay, so here we have POH. We're going to do this a couple more times with different letters. So POH is essentially minus the log of the OH minus concentration. And so at 25 degrees Celsius, POH equals minus the log of 1 times 10 to the minus 7, which is 7.00. Okay. These can be useful. Sometimes you want to work in POH, sometimes you want to work in pH. So let me show you both. So there's really, I guess I want to just say, there's really nothing special about pH and POH. It's just another way of reporting a concentration. Sometimes these numbers are a little hard to say, right? 1 times 10 to the minus 7, it's a bit of a mouthful. So if you can report a pH equals 7, that's slightly more convenient. And so that's why we've started to use, many years ago, started to use pH. Okay. So H plus and OH minus are related. They're related by the Kw. And if you recall, Kw is the equilibrium of water. Well, let me do it this way, since I've written it as H plus. Okay, so the equilibrium, water as a reactant, water dissociates slightly to H plus and OH minus. We give that a special value, that's our Kw, and this is equal to what we've already have written over there, H plus times OH minus. So that's just the products. Okay. So if we know the H plus concentration, we know Kw, right, at a given temperature. At 25 degrees Celsius, it's 1 times 10 to the minus 14. Okay. If we know H plus, we can calculate OH minus with that. If we know OH minus, we can calculate H plus. So solving for both of those, we have H plus equals Kw over the OH minus concentration, or OH minus equals Kw over H plus. Everyone okay with that? All right, so here's our other fun way of taking minus the log of something, okay? There's another convenient way of relating the OH plus and OH minus concentrations that is through the, often through the pH. Usually that's the number that we calculate. But we're going to take minus the log of both sides of this equation and come up with a new equation. So let's go ahead first and plug in our value of Kw at 25 degrees Celsius, which is 1 times 10 to the minus 14. And now I've switched to H3O plus. They're interchangeable here, H plus and H3O plus. Let's take minus the log of both sides. So we'll have minus the log of 1 times 10 to the minus 14 equals minus the log of H3O plus times OH minus. And if you remember the rules for logs, which I often don't, so I won't be offended if you don't either. When we multiply something within a log, we end up adding them together to break them out of the log. So we have on the right-hand side minus the log of H3O plus minus the log of OH minus. And on the left-hand side, minus the log of 1 times 10 to the minus 14 is 14. We could put some sig figs here if we want. Often we just assume that's 14, just 14. What's the number called? Slipped my mind. The one that doesn't have any units. You know what I mean? You don't know what I mean, but that's okay. Just assume it's a number that is 14 and even. Okay. I'll think of it eventually. Okay, but what is minus the log of H3O plus? pH. And what is minus the log of OH minus? POH. And so we can relate pH and POH through this equation. pH plus POH equals 14 at 25 degrees C. Okay. Questions on that? We're really hitting with all the fun acid-base stuff. It's really invigorating. I'm feeling it. Okay. I have a blank slide here. Okay, I'm going to give you all a chance to calculate based on an initial concentration of H plus, the pH, the POH, the OH minus concentration, and then starting from pH, the other three things, okay? Grab some calculators, work with your neighbor, and give these a whirl. had some good questions. So let's kind of work through these together. There's we're asking you to solve for 3 different things given H plus concentration here on the left-hand side. So the first thing that I would do, and it doesn't necessarily have to be what you do, is I would calculate the pH. So to find the pH, I would take minus the log of the H plus concentration, 0.000015, and end up with 4.82. Okay. So I had a good question that was, if we're at 25 degrees C, does that mean that H plus and OH minus concentration is the same? If we're at 25 degrees C and there's nothing in solution except water, then yes, that is true. But what these problems are assuming is that we've added some acid to the solution or we've added some base to the solution. Okay. So I guess to be kind of a little bit more clear on this side, we can say we added acid to get the H plus concentration equal to 0.000015. And on the other side, we can say we added base to a pH equals 11.51. Okay, that's a basic solution because it's greater than 7. pH is greater than 7. All right. So the next thing we could do is calculate pOH, or we could calculate OH minus. I might say calculate pOH using the equation 14 equals pH plus pOH, and plug in the value for pH. And so we would have 14 minus the pH equals pOH. So 14 minus 4.82 equals 9.18. There's actually 2 ways next of solving for OH minus. I will show you one that probably was the most obvious first, and that is that OH minus, actually, hang on. We're going to put this here so as not to confuse things. OH minus equals KW over H plus. Okay. Most of you tried it this way, or we're getting there? No? Okay, that's fine. We'll have 1 times 10 to the minus 14 is our KW, divided by our H plus concentration, and we would end up with an OH minus concentration of 6.7 times 10 to the minus 10. Oh. What did I do? Go away. Okay, well that's going to live there now. All right. There's one other way to calculate OH minus if you know the pOH. So we said that pOH, or pH, equals minus the log of its concentration, right? Could do the anti-log on both sides of the equation. And so, here, you don't know, I didn't say what I was doing there, sorry. If we do 10 to the minus pH, that's equal to the H plus concentration. The minus sign in front of the minus log has to go over to the other side. So this minus sign has to go here in order to make this the H plus concentration. Otherwise, it would be the negative H plus concentration, okay? Which is still usable. You can just get rid of the minus sign. So that is another way of calculating H plus or PO8 or H plus or OH minus. Okay, which may not have been particularly obvious initially. All right. Any other attempts or things you want to talk about, if they worked or whether they would work or whether they wouldn't work? Questions about anything? Yeah.
This is going back to these acids and piggybacking off something else said, but if we look at a formula and one of the reactants is like a cation, like 3+, could we automatically assume that's the Lewis acid?
Yeah, so if you've got a reaction and you know it's an acid-base reaction and you're trying to identify if or which is the acid, you can pretty much assume that it's the cation.
Okay, all right.
But you'll want to make sure that that is an acid-base reaction first. Yeah. Yep. Yes. Okay, so what you're finding is that if you do 10 to the minus 9.18, you get a different value than if you do KW or H. How different are they? Okay, so it would be, what did you get where 10 to the minus POH?
I'm sorry, it is 6.6 times 10 to the power of
6.6 times 10 to the minus 10. Yeah, that makes sense. I mean, there's some rounding that goes in, especially when we're dealing with logs. A little bit of rounding in the POH is going to make a big difference in the concentration. I wouldn't worry about it. I think those numbers are essentially the same. So I think we're okay with that. I would call them, both are okay. Yeah. Yep. Yeah.
So since we can just do like the 10 or negative power thing,
Yes.
what's gonna be like easier? So like what's the purpose of doing it like the hard way with the KW?
Okay, so when would we use KW and dividing by H plus to get OH? Well, I guess if you didn't want to calculate first pH and then POH, let's say you only needed, you had H plus and you need OH minus concentration, you can skip calculating pH to POH and then just use KW, slightly faster that way. That's kind of it. Yeah, just different methods to get you the same number. You can choose your preference. Other things? Did we try the second one? Okay. So here you're given a starting pH. We're asked to calculate H plus. Okay. In my notes, I did concentration of H plus equals 10 to the minus 11.51 to get 3.1 times 10 to the minus 12. Okay. To calculate OH minus, so now I would say the easiest way to go about that is OH minus equals KW over H plus, if I'm going in order here in my list. So we'll have 1 times 10 to the minus 14 over 3.1 times 10 to the minus 12. Which will give me 3.2 times 10 to the minus 3. Okay, and then the POH, I always like 14 equals pH plus POH. It's nicer numbers to work with, so 14 minus 11.51 is equal to the POH. Okay, and that gives us 2.49. All right. So looking at these numbers, on the left side we have an acidic solution. Our pH is 4.82. On the right side, we have a basic solution with a basic pH 11.51. So when we think about what the definition of pH and POH are, they're effectively telling us the concentrations. So the bigger the concentration, the smaller the value of POH or pH. So when we have our basic solution with a POH of 2.49, that's good, right? It's a larger concentration of OH minus, so our pH value should be above. And approximately, to kind of do your math check, if you add up the exponents on H plus and OH minus concentrations, you should get 14, 15, somewhere in there. That kind of helps make sure you're doing things correctly. If you get like 5, you've probably done something wrong. All right, other things. Yes?
How did you get KW?
KW is because it's the value is a constant at 25 degrees C, 1 times 10 to the minus 14. I think it is part of the information provided on the exam, but we also double check on that. Yeah.
What would happen if you were like,
If you're given a different temperature and asked to do all of that, you would have to be given a different KW.
but like that would be given?
Yeah, that would be good. And then you would have to adjust at 14 when we're getting more KW. All right. Next time, we're going to do a review. Maybe on the demo.